Let's keep going over basic logic gates, and this time we're going to cover a little bit of gate substitutions. What is the behavior of this circuit? We have a bunch of logic gates represented here. The insides of it becomes a little bit tough to follow and understand which gates are we implementing in a circuitry like this. So we abstract and we have something like this, much easier to follow right now, which that states the importance of the level of abstraction. Right now we are no longer going to the level of the transistor inside of the gates. That's what we did in Intro to Mechatronic Systems 1. Intro to Mechatronic Systems 2, we are going to spend our attention on the gate level. Not only that, we're also going to have truth tables to represent that information of those logic gates. Then we have Boolean Algebra, invented by George Boole in the mid-19s, and it's just a set of rules that we have based on human reasoning, and we have a bunch of symbols that we use. We learned these ones on previous videos for the logic gates that we have, and we also have a couple of rules or properties that we can use to manipulate the Boolean expressions. These are just a couple of them, and or an exclusive or. These dashes over here, these are negations. They are complete lines on top of the letter, so completely here on the A, on the B, and A and not B, for example. And if I negate twice, I get just the gate. These are going to be useful when you are simplifying your Boolean expressions by massaging the Boolean equation. And let's go over these gate substitutions. So sometimes we don't have gates available, for example the NOT gate, and how can I implement the NOT gate now with other sets of gates that I have available? So one way of doing this, there are possible solutions, is to actually short circuit the inputs of an AND gate and the inputs of an OR gate, and now this is behaving exactly as a NOT gate. One input, one output. And let's look a little bit closer here, and I'm going to design the truth table for your NAND gate. So let's put text here, and the truth table is if I have a 0 and a 0, I get a 1, a 0 and a 1, I get a 1, 1 and 0, I get 1, and 1 and 1, I get 0. This is a truth table for the NAND gate. Notice that by short circuiting the inputs, I'm looking at this part of the truth table and this part of the truth table. So if I have a 0 coming here, I get a 1 on the output, and if I get a 1, I get a 0. And that's how your NAND is inverting the values or working as a NOT gate. Similar to your NOR gate, it's going to have exactly the same behavior, and there are other ways of doing NOT gates with other gates. Another important substitution was developed by August de Morgan. He developed two theorems that tells you that if I negate the inputs of an AND gate is the same thing as negating the output of an OR gate, and vice versa. If I go here and I negate the output of an AND, is the same thing as negating the inputs of OR. So remember that the common mistake is to actually go from this one to the bottom or this one to the bottom. That's not valid, but this relationship from left to right is valid either on theorem number 1 and theorem number 2. There are also, this is the same thing with the Boolean expressions, so negating the inputs of my AND is the same thing as negating the output of the OR gate, and negating the output of an AND is the same thing as negating the inputs of an OR gate. And this is the Boolean expression. So these are called the Morgan's theorem. And we also have this table with some properties that you can apply. So once again, these will seem like dots, but they're lines. They're on top of the letters. On your PDF will look much better. And these theorems are good for us when we are simplifying Boolean expressions. We could apply some of these rules and make life easier.